Hi, and welcome back to this lecture. So this is the first lecture, and today I'll go over the essential math that you would need to understand the basics of quantum computing. Uh, as per the plan, I have decided to only dedicate this one lecture to the math review for quantum computing. So I'll be pretty quick, and I'll mainly mention the things that you need to know, uh, the math you need to know to get started with quantum computing. I'll mention the key topics, and you could look at it, from different resources. Since it's going to be around 35 minutes of lectures, I'm not going to be able to cover all the topics, but I'll try to mention all the topics that you would require so that you could look them up differently at your convenient time. Okay. So two topics uh, which we will be covering, which I'll be mentioning rather, will be complex numbers and linear algebra. So the essential required math will be uh, from complex numbers and linear algebra. Okay, linear algebra. So again, these are vast domains of math, complex numbers. I remember when I was learning it for the first time in my undergrad, it was like an entire semester course. And linear algebra, I think it was distributed into semesters, basics and then advanced. So we'll only look at the essential topics from complex numbers and linear algebra that will be useful for this entire course of quantum computing. So let's get started with complex numbers. Okay, so complex numbers. Uh, as you may recall, it all starts with this number I, which is the square root of -1. This is called as iota. Okay, and it is defined in a way that I square equals to -1 and I to the power 4 equals to 1. Okay, uh, and starting from this, the definition of complex number goes like this: Z is the complex number, and it is defined as A times IV, where I is the iota. Okay. So A and B here are the real and imaginary parts of real part. A is the real part, and B is the imaginary part of complex number Z. That means A and B are essentially real numbers, and I write it in this following way: that A and B belongs to this symbol. This E symbol is denotes belonging to the set of real numbers. Okay, so this is just another way of saying A and B are real numbers. A and B are real numbers. So note that Z is not a real number. Okay, Z is not a real number, but A and B are real numbers, using which Z is constructed, not a real number. Okay, so this is the most basic definition of a complex number. Z equals to A plus IB, and we represent it in a complex plane, right, which looks like this. So we have a complex plane. This is the real axis, and this is the imaginary axis. A complex number is denoted here in this plane. Okay, so it could look something like, let's say the complex number is here. Okay, so I can put an arrow to it, and if I take the projection of this vector, on this axis, then this is the real part. So this would be A and this would be B. Okay. So A and B denote the real and imaginary part of the complex number Z. And I can see that this forms a triangle now, right angle triangle. And let give a name to this angle, theta. So I can see from here that tan of theta is going to be B by A, right? Perpendicular by base. And accordingly, theta would be tan inverse B by A. Okay. I can also see that this arrow, which denotes the complex number, um, has a length, right? And that length is nothing but the hypotenuse of this right angle triangle. So I denote that length as Z mod. So this we call as the modulus of G when you put two bars on the left and right side of it. And this is nothing but A square plus B square root 2, right? So it's like a electromagnetic wave, the phasor of an electromagnetic wave, or a vector. Okay, so a vector can have a length and it can also have an angle defined with respect to the x-axis. In terms of phasors, so phasors have an amplitude, right, which is the magnitude, and then it has a phase. So here, theta is the phase, and this z mod is the length of the vector, or the modulus of the vector. And in this way, we can also represent z as z modulus times e to the power I theta. Okay, so this is another representation of the complex number. That means the complex number can have two representation. One is this and two is this. Okay, the first representation here. So representation 1 is called as Cartesian representation. Okay, so this is Cartesian or rectangular. And representation 2 is often called as polar representation. Okay, polar. Okay, so we see that we can either write z as a plus ib or z as z mod times e to the power I theta, where z is the modulus, z and 2 bars is the modulus, and theta denotes the phase of the complex number. Okay, so far so good. Next, we define something called another thing is, so let me put dot. So we have this is a parameter, this is a parameter. Then we define something called the conjugate of a complex number. Okay, conjugate of a complex number, and that is z bar, and z bar will be a minus ib. If z is a plus ib, then z bar is a minus ib. So this is another definition to remember. And once you know z and z bar, you can calculate a few things. For example, three things are important here. So one, if you multiply z and z bar, okay, what you essentially get is z mod square. Okay, so this is something important to note. Z into z bar is z mod square. All right. We can also quickly check it. So z into z bar would be do it small a plus ib. I hope it's still, yeah, a plus ib times a minus ib, right? So this would give me a square, and then minus I times ab, and then plus I times ba, and then I into minus I. So I square equals to minus 1, right? minus I square would be plus 1 plus b square. So these two terms cancels, and what we get is a square plus b square. And this is nothing but z mod square, right? From this definition. Okay. Maybe I should also just highlight this too here. So theta equals to this, and c equals to this. So this is also an important formula. We can also see that if you take the addition of the two number, so if you take z, I don't want this size. If I take z plus z star, then it becomes 2 times the real part of z. And if I take z minus, sorry, I can see z bar, then it becomes I times 2 times imaginary part of z. So if you want to calculate the real part and imaginary part of z, then you could also write that the real part of z is nothing but z plus z bar, okay? Z plus z bar. Just a second. हाँ ठीक है छाड़ी गई हाँ ठीक है छाड़ी गया I'm really sorry about it, guys. It was very important for me to attend. So real part of z is can be given by z plus z bar over 2, and imaginary part of z can be calculated as z minus z bar over 2. Okay, so these are a couple of more definitions to remember. And another thing which is often useful, can you tell me what will be 1 over I in terms of I? Please take a moment to calculate. So what will be 1 over I in terms of I? How else can you write 1 over I in terms of I? Okay, I believe you tried on your own. So this is nothing but minus I. Okay, how can you check it? Well, just multiply I on the top and the bottom of this fraction 1 over I, and you will get it as minus I. Okay, so I guess these are the most essential parts of the complex numbers that we will need. For example, we'll often need the magnitude of a complex number because that denotes the probability. Okay, we'll also need the phase of a complex number. All right, so these are some essential concept of complex numbers that we will be requiring time to time. And yes, we'll also need to know this identity of complex number. This is called as the Euler identity or Euler's rule, which says e power I theta is nothing but cos theta plus I sine theta. All right. If that is so, then you can check what would be e power minus I theta. Please pause and take a moment to check it. All right. So the answer will be cos theta minus I sine theta. Okay. And how can you check it? You can check it in the following way. If you start from this definition, okay, then what you can take, you can write e power minus theta. E power minus I theta is nothing but e power I times minus theta. Okay, so in this definition only, in the first definition, okay, so this is the definition. Remember, in this definition, what I'll just put minus theta in terms of theta. So this becomes cos of minus theta plus I times sine of minus theta. And we very well know that cos of minus theta is cos theta, and sine of minus theta is minus sine theta. So it becomes cos theta minus I sine theta. Okay. If you do a little more math, then you can find out that cos theta can be written as e to the power I theta plus e to the power minus I theta over 2. And sine theta will be e to the power I theta minus e to the power minus I theta over 2 times identity. Okay. These are some useful, uh, oops, I think you could not see this part. I'm sorry about it. So what I did, I took e power minus theta, okay, and I wrote it as e power I times minus theta, I times minus theta. Okay, so I just took the definition, and in place of theta, I put it as a minus theta, and then cos of minus theta and sine of minus theta. We know its value. Cos of minus theta is cos theta, and sine of minus theta is minus sine theta, right? So we get cos theta minus I sine theta. Okay, all right. And we can also get the value of cos theta and sine theta from this. Okay. Few more things to remember is if you take theta equals to pi, then you can see that e to the power I pi would give you -1. You can just plug in the values of theta in the cos theta plus I sin theta value and check this. And this is also one of the most foundational equations in mathematics, e to the power I pi equals to -1. I check now as a task, what would be e power pi by 2 and e power I pi by 4. Okay. All right. I think you got the answer already. So e to the power I pi by 2 would be sine pi by 2 plus I times cos pi by 2 plus I times sine pi by 2. Cos pi by 2 is 0. So this would become just I. And e to the power I pi by 4, this would become 1 by root 2, 1 plus I. Okay. These are some definitions that we'll be using later, because there are some quantum gates, okay, the logic gates of quantum computer, which will need these values. That's why I mentioned them. All right. That's all we'll be talking about complex numbers. Let's go to the concepts of linear algebra, and let me try to mention the essential linear algebra that we'll be needing in this lecture, in all our QC lectures. Okay. And anyway, I mean, linear algebra is an excellent field of math, and the more of you know, the more you can apply it to various other fields, from data science, some optimization problems. Also, Python is constructed over linear algebra, MATLAB, of course, and quantum mechanics, quantum computing. All these things are there any day. So we are going to look at some linear algebra concepts now. Oops, I need black color. So essentially, I want you to brush up what are vectors, what are matrices, how we multiply matrices. Okay, then taking conjugate and transpose of matrices. Okay, next will also require eigenvalues and eigenvectors of matrices. Okay, all these things will be super useful. It will also be helpful to know about diagonalization of matrices. Okay, then knowing about the vector space and basis of a vector space. This thing will be, I think, very essential. I don't remember anything else. Yeah, we may need Gram Smith and other things, but for the time being, I'm not mentioning them because they are not super essential for quantum computing, at least for the next few days. So I'll just stop here, uh, mentioning about the different topics of linear algebra. So I believe you know vectors. Okay, they are just put in square boxes, right, and some numbers. And you also know about matrices. And I guess you also know how to multiply two matrices, right? If I'm multiplying ABCD with E, F, G, H, then this would be A times E. The first element would be AE plus BG. The second element would be AF plus BH. The third element would be CE plus DG. And the fourth element would be CF plus DH. This is how you multiply two matrices, right? Yeah. And if I have two matrices of the order M cross N, then the other matrix must have the order N into something. Okay, and this would give me a matrix of size M cross P. Okay. Um, just a sec. Yeah. So the next thing to look at would be uh, conjugate of a matrix. So if I have a matrix A, B, C, D, and this A, B, C, D could be complex number, real number, whatever. If I want to look at the conjugate of this matrix, then they are going to be just, the conjugate of all the elements A, B, C star, D star. Okay. And if I want to take the transpose of a matrix or a vector, what happens? Only the row and the columns, they just flip. So what will be the transpose of this? This will become AB and CT. Okay. So this is conjugate, and so this is conjugate, right? Complex conjugate. And this is transpose. Now we define something called this dagger. Okay, dagger of a matrix. And in that case, it's very much used in quantum computing. So when you mean dagger, it is actually transpose and then complex conjugate. So it is something like ABCD matrix. You take the transpose and then you take further the complex conjugate, which is same as doing it the other way. First taking the conjugate and then taking the transpose. Okay, and what would be the outcome? The outcome would be if we take first the conjugate ABC star D star, right? And then we need the transpose of it. So ultimately it becomes A star B star C star D star. Okay. The next important concept would be to look at eigenvalues and eigenvectors, right? So uh, if you have a matrix A, so matrices are often designated with capital letters, right? A. Then to find eigenvalues, we usually solve this. We take A times minus lambda times identity matrix. So if A is of order 2 cross 2, so that's 4 elements, then identity matrix will also need to be 2 cross 2. Okay. And then we take the determinant of this and equate it to 0. And this gives in some equation. Okay. And lambda here is the eigenvalue. So lambda here is the eigenvalue. And this equation, would finally give two values of lambda. I mean, if A is 2 cross 2, then it should have two eigenvalues. If A is 3 cross 3, then it should have three eigenvalues and so on. And this would give you your eigenvalues. So the degree of the equation would depend upon the size of A. So if A is a 2 cross 2 matrix, then this equation would be a quadratic equation so that you get two roots for lambda. Okay, so eigenvalues, which are nothing but, roots of the equation. And then the definition of eigenvectors is this, that when you apply A, let's say X is the eigenvector, then it should give you lambda times x. Okay, so what happens is when you apply A to a vector x, okay, you apply matrix A to a vector x, all it does it just scales the vector x by an amount lambda. So if your vector is of this length, lambda gets multiplied, then it just scales in a certain direction. Okay, so the direction of the vector doesn't change, it only gets scaled in that particular direction. Okay, so here in case if you have two eigenvalues, then you will have two eigenvectors, right? So it could be something like a of x1 would be lambda 1 times x1, and a x2 will be lambda 2 times x2. So you can just assume x1 to be some random number, let's say ab, and then you can compute from this equation what are going to be x1 and x2. So this you could check out if you have completely forgotten how eigenvalues and eigenvectors are calculated. You can check out any book, any reference, or any YouTube videos are fine. There are excellent materials on this. I will strongly encourage you to find the eigenvalues of the following. Eigenvalues of the following matrices. These are in fact very important matrices. Just for practice, you could check the identity matrix even. Okay. And remember, all these metrics which I'm writing now are 2 cross 2 matrix. So they will be having two eigenvectors and two eigenvalues. Then you can check 1 minus 1 0 0. Then you can check 0 minus I here is nothing but the iota. And you can also check this 1 by root 2, 1 by root 2, 1 by root 2, and minus 1 by root 2. Okay. So yeah, this I just leave to you as a homework problem. Okay, you can check eigenvalues of the vector. All right. Another thing to mention is vector space. So the vector space is again very big topic, and people often teach vector space for one semester. But I'll just suggest you to read about vector space. You can find things on YouTube or something. But essentially, it's a space which contains vectors. Okay. And let's say you have a vector space where you have 4 vector v1, v2, v3, and v4, and I can write v2 as some c times v1 plus some d times v2, d times v3. Okay. I can also write v4 as some other number. C, D are here any random numbers, 2, 2.5, 3, 3.5. Okay, any complex number. And v4 I can write as, let's say, some a times v1 plus some or let's say some b times v3, and I can write v1 as, of course, 1 times v1, and v3 as, of course, 1 times v3. So essentially what I'm telling you here, that just by using v1 and v3, just by taking their linear combination, so this is here the linear combination, right? Some number times v1 and some number times v3. So this is linear combination. I can represent all the elements of this vector space V. Okay. So you have a vector space and it has some vectors inside it. You take some vectors from this vector space, and using this few vector space, by taking their superposition, you can represent any other vectors of that vector space. So this set of vectors, this set of vectors, in this case v1 and v3, which can alone by their linear combination represent all the other vectors they form the basis. Okay, so here V1 and V2 forms the basis. Here V1 and V3, sorry, forms the basis of V. Or we also say that V1 and V3, this basis or spans V. So spanning V means that they alone can represent the entire vector space, by the linear combination. So this is the idea of basis. Okay, basis is something super important. For example, in quantum computation, 0 and 1 forms the basis. Another basis, 0 and 1 forms a basis, and this basis is called as computational basis. There's another basis called as Hadamard basis. We'll look at them in some other lecture in detail. Okay. The last topic that I want to address here is diagonalization. Okay. And diagonalization is something very important. Again, we might not need them immediately in our course, but at some point I think we'll need them. But it's anyway good to know. So let's say A is a matrix. Okay. Then and lambda is its diagonal matrix. So this diagonal matrix is actually, lambda 1, lambda 2, lambda 3. So all the eigenvalues in the diagonal, and everywhere else it's 0. Okay, so this is the diagonal matrix. So you can represent A as some vector V times this diagonal vector times V inverse. Okay, so what is V? So V is nothing but you can call it as eigenvector matrix. Sorry, V is not a vector, it's a matrix again. So this is basically one matrix times this diagonal matrix times another matrix. Okay, so V is here the eigenvector matrix, and lambda here you can call it as eigenvalue matrix or the diagonal matrix, eigenvalue matrix. And this formula can also give rise to another formula, which would be, you can write this as V inverse times A times V. Okay, so these two are equivalent. You can just prove it on your own. Now, why do we need to know about this diagonalization thing? We need to know this because they are really helpful. And why are they helpful? Suppose you want to calculate the nth power of A, then what happens? Nothing changes, but the eigenvalue, sorry. So let's say you have this matrix, and this matrix is evolving in a way that, or this matrix is changing in a way that you want to know the second power of A, or third power of A, or fourth power of A, or nth power of A. Then you would see that the eigenvectors don't change. Okay, I mean the eigenvector of A and the eigenvector of A square would be the same. Eigenvector of AQ would be also the same because the eigenvector matrix here V is not changing. What change is only the eigenvalues, only change. And how do they change? They just change by the power. So if you want to know the the third power of A, let's say, for example, the third power of A, what is going to the A3, then all you need to do, you have already calculated the eigenvectors. So from that, you can have the eigenvector matrix. And then you have the eigenvalue matrix. So you just take the third power of it. Okay. So if you have the eigenvector like lambda 1, lambda 2, okay, let's say this is the eigenvector matrix, sorry, eigenvalue matrix, then the square of it would be, lambda 1 square, lambda 2 square. Okay, very easy. And then this. Okay, so that's why diagonalization becomes very important, because you can know how your matrix would evolve just by evolving the diagonal matrix or the eigenvalue matrix. All right, it's already time, and I would like to stop here. But essentially, we covered quite a few things. We covered about complex numbers, how they're represented, how to find their real and imaginary part from z and z bar, from the complex number and its conjugate. We look at Euler formula, e power I theta equals to cos theta plus I sin theta, and then we saw the legendary equation e power I pi equals to -1. Then we looked at vectors, right? So vectors and then matrices, and you can multiply matrices. There's this idea of eigenvalues and eigenvectors, which become very useful. And using them, you can also diagonalize things. And additionally, we looked at what is the basis of a vector space. A vector space is a space which contains vectors, and few vectors in this vector space are important in the sense that they can be used in their linear combinations to construct all the other vectors there. So yeah, I'm sorry again for keeping this lecture so tight and putting a lot of information, but I'm sure you have got something from here, and you would look deeper deeper at these concepts from some other resources. But yeah, essentially all these things will be needing for our future quantum computing lectures. So until then, until we meet next, take care, bye-bye, and revise this concept and take your time to learn this in a bit of more detail. Bye-bye.